So we were discussing here how implementing thermal mass can reduce a lot the needing for heating and cooling. So if we take the following example, let's say during the day, during a summer day, we have the thermal mass will be able to store the excess of energy. So we don't need to operate the HVAC, let's say, in order to maintain a comfortable temperature. Then from 5 p.m. to 11 p.m., the thermal mass will store back the energy released in order to allow an acceptable temperature within the space. After this, the heat release will be reduced with time. And if you study the heat release, it will be optimal in the first few hours. And with time, it will be reduced because you know that the heat release is related to the difference in temperature between the thermal mass and your inner space. Okay, so whenever you have with time, this temperature will decrease because the thermal mass is giving energy. So the temperature of the thermal mass will decrease until at the end a certain stage of equilibrium where the temperature of the thermal mass will be equal to the temperature within the space. So you don't have any you will not have any more a release of heat to the room. This will happen nearly around, let's say, in this case, 6:30 a.m. So after 6:30 a.m., from 6:30 a.m. to 10 a.m., you might need to have the intervention of your ventilation system. While during the remaining hours, the thermal storage system was able to provide you with the required energy, so you don't need to operate your ventilation system. So this is an example where we can see that the number of hours that will require the use of heating and ventilation system will be much lower whenever we have an appropriate thermal mass. Now, in the following figure, we can observe the thermal mass effect in heating season. So we can see that if we don't have the thermal mass, the fluctuation in temperature will be really high. Here we are comparing several graphs. We have first, the largest fluctuations correspond to the outdoor temperature. Of course, the indoor temperature will not have the same profile because you have an insulation. The envelope will play a certain role in reduce. Okay, so we were saying that the thermal mass will play a big role in reduction of temperature variation. The largest variation will be observed for the temperature in the outdoor space, because in the outdoor space you have very high temperatures during the day and very low temperature during the night. While if we consider, let's say, a light timber frame building, so it's characterized by a low light thermal mass building. So of course, it's true that the light thermal building will not have a good performance, but of course it will lead to a certain reduction in. So if we observe here the dashed line, the dashed line corresponds to the light timber frame building, which is characterized by a low thermal mass. We can see that it's true that we have a reduction in the temperature variation, because compared to the outdoor environment, we have a lower maximum and a lower minimum in absolute value. Okay, but still we have high fluctuations within the space. This is because of the low value of the thermal mass. To enhance the behavior of the thermal mass, we can use a heavier thermal mass. So for a heavy building with external insulation, we can see that this pattern of variation is much better. The fluctuation within the indoor space will be much lower. So we have a much lower maximum and a much lower minimum in absolute value. So we can see that in this case, the thermal mass, when designed appropriately, can reduce a lot the fluctuation in temperature. Now, if we use a heavy building set into and partially covered with earth, so if we optimize more the use of thermal mass with other strategies, we can reach nearly a constant temperature within the space.
Professor,
Yes.
what do you mean by partially covered with earth?
Okay, this means that you can, let's say, use vegetation to cover your house. You can and whenever you select the orientation, you can put it in a way to reduce the exposition of your building to solar rays that are not desired, etc. Yani you combine the presence of thermal mass with other strategies that will protect your building from the external environment. Okay, this partial covering can be using shading, it can be using vegetation, etc. Okay.
Yes.
Now, a large thermal mass within a building can delay its response to heat sources, such as solar gains, like the thermal lag effect. So what do we mean by this? If you observe the pattern of variation of temperature, you don't have only reduction of delta T, but also the response to external variation will be reduced. What we mean by this, if you observe the increase of temperature here, it will start at early stage here. On the other hand, if you take the example of, for example, the case of heavy building with external insulation, you have a delay of the increase of temperature. So it will start nearly starting from this level. So not only you will reduce the temperature variation, but you will create a lag effect. So you have not a spontaneous response to thermal change. You will have a delay in the variation of your temperature, which will lead to a more comfortable feeling, because you have during the day you delay the increase in temperature, and during the night you will allow to have acceptable temperature even if you have low external temperature in the external environment. Now, as we mentioned also, we can benefit from landscape strategies. So landscaping strategies can facilitate passive heating by allowing solar heat gain during winter and providing shade during summer. So we can, for example, as we discussed before, we can use street trees in order to provide shading for our building in zones where it's necessary, like in east and west facades. We can work appropriately with street alignment when we want to design several houses at the same time. We can use of landscape buffer zones. So this what we discussed now about covering the building in a optimal way in order to create a buffer to overheating. We can use vegetated green roofs and walls. So we have seen a large use of green roofs recently in Lebanon. And also, we have some limitations for this, so we should take into consideration the space that we can play with. We should consider maintenance and irrigation whenever we have vegetation. We have high buildings problems of weight, wind, pressure, and irrigation. So we might have some blockage effects to these strategies, but we try as possible within the design to overcome these problems by appropriate design of the system. So for example, here we can see how we can protect. So in these buildings, we create protection of the building from sun, wind, and precipitation using vegetation. So landscape can play a major role in passive design. Passive solar buildings are usually elongated in the east-west direction, so that a large south-facing surface is presented to the low winter sun for solar heating. Small east and west-facing surfaces are presented to the northerly rising and setting summer to reduce unwanted solar gains. The aspect ratio east-west dimension divided by the north-south dimension should be at least 5/3, and much larger values are appropriate for large dormitory-like structures. So here, we are giving some recommendation about the orientation. Already we know that in Energy Plus, we can study several orientations, but in order to limit the number of orientations we try in Energy Plus software, we know from these recommendations how to consider in general, it's better to take this recommendation into account when studying the orientation. So as mentioned here, and we'll see in an example, we should try to ensure an east-west dimension divided by north-south dimension equal at least to 5/3. And we can have larger value in order to enhance the effect of orientation on the building performance concerning energy consumption. In ideal case, passive solar buildings should be no more than 2 zones deep in the north-south direction. To understand more what we mean by this, we can consider the following figure, okay? So we can study, if you want, the orientation of the building and how we can consider the ratio. Because we desire a high, let's say, a high glazing surface on the south facade, we can have a large area on the south facade compared with the ones in the east and west orientation. Okay, so this is why we can optimize, if you want, the orientation and the shape of our building in order to enhance the performance. Plus, also, we should consider the effect of envelope area to volume ratio on the energy efficiency. So we try also to have a smaller exposed area relative to the volume in order to reduce heat losses from the building to the external environment. Now, the two-zone limit on depth generally allows solar heat collected on the south side of the building to be transported for use to the north side. This is why we try to have a short distance between south and north, as we discussed, and we increase the length in south direction, thereby improving thermal performance. Orientations that depart from true south by up to 30 degrees are permissible, and performance penalties will usually be less than 10%. So in general, we have a flexibility because sometimes, depending on the architecture, we might need to change a little bit the orientation. But if we change it a lot, we might have drawbacks. An easterly bias is preferred in applications that require a rapid warm-up in the morning, while a westerly bias will sometimes improve the performance of buildings that are occupied in the evening because of the improved phasing of heat source and heat load. So again, it depends on the type of building you are designing. So you have, let's say, for offices, the majority of occupancy time is during the day. While if you have for residential buildings, the majority of occupying hour is during evening. So depending on this, we can change the orientation because in the offices, we are mainly interested in the hours during the day, while for residential buildings, we are more interested in hours during the night. So this will affect also the selection of the appropriate orientation. And this is why, as we have seen last time when we studied the Energy Plus software, we should give it the occupancy schedule in order to optimize the design and select the appropriate orientation and appropriate selection of materials for our building. And always, we try as much as possible to reduce the complexity, because for the same area, we try to have, if you want, the efficient layout will be the one without a lot of angles and without a lot of curves. Okay, so if we compare these two, it's just a straight triangle instead of having several changes in directions. This is an inefficient layout, while this one is much more efficient. So complex layouts will lead to more corners and joints, which will lead to leakage of energy. It will also create more surface areas which can lose heat. Now, windows that are not facing south should be kept small while complying with local building codes. So we already discussed, for example, that in ASHRAE, you can find recommendations about the design of, let's say, windows. What are the U values required? For each climate, we give appropriate design. So let's say the type of windows used in Lebanon will be much more different than the one in Arabi Saudi or the ones in United States. So for each country, you have like a code to tell you what are the recommended values of installations that should be provided. Particularly in the colder climates, it is best to place most of the non-south window area on the east or west side of the building to take advantage of winter solar gains available during the early morning and late afternoon. In this case, all windows, including those facing south, should have at least 2 glazing layers because of the extreme cold climates. And in the harsh and very harsh regions, triple or even quadruple glazing should be considered in order to reduce heat loss from between the inner and outer environment. Especially in the warmer climates, drapes or better still, movable opaque covers or shades are recommended as means to prevent unwanted sunlight from entering the windows during the summer season. So here we can see, as we discussed also before, some landscape strategies. So vegetation can play a major role. So for example, here, let's say during the summer, the vegetation will play a blocking effect. So it will act as shading, reducing energy transmission from the sun to the building. While in winter, we want this energy to come in. And we know that in winter, the trees, we have the trees will be denudated. So in this case, we don't have any more papers on the trees, and this will lead to help the sun rays to come in the building. Here we can see, now we will discuss active solar systems. So in active solar systems, as we mentioned before, we need an external intervention to help the functioning of the system. This external intervention can be by using pumps, for example, to circulate water. Here we see an example of a thermal storage assisted with solar collectors and pumps in order to control the circulation of water. So for example, if we consider the system, we are combining solar energy with thermal mass. So the components of the system are as follow. You have first the PV arrays, the PV panels that are mounted on the roof. During the day, you have solar energy that will hit the solar panels, and then energy will be absorbed by these panels. Now, what will happen within the panels, you have like a heat exchanger allowing circulation of water. So water will circulate through the panels, and it will take energy absorbed from the panels to heat water. Now, the heated water can have several use. First, if you need to use it directly, okay, it will you have a direct connection, let's say, to daily usage of water, like for shower or for domestic use, etc. Also, in case you don't need it now, you can just use it to you can store it, let's say, in a tank to be used after. Or also, if already the tank is full, you can pass it through through, if you want, a underfloor heat exchanger where it will release heat to a thermal mass. Okay, so the main components of this system are first the solar collectors, which will collect the energy. You have here a thermal mass that can be used for energy storage. You can have also a certain air handling module. So if you are circulating, let's say, you can circulate air or you can circulate water. It depends on the fluid, the application, if you want to use it for heating and ventilation, or if you want to use it for water use. So you can have, depending on the case, you can have fluid that is circulating, you can have water, or you can have air. So here, for example, you can have, let's say, a reservoir that can collect your water in case you are using water as system. You have also an electrical duct heater that can be used in case solar energy is not enough. Your water can pass through an electrical system that can help into heating it. You have also a control unit that can specify if I need to circulate water or not. So the control unit will decide on the amount of mass flow rate that can circulate through your system. So during the day, you will have circulation, while during the night, the sun is not available. You don't circulate water in your system. So during the night, what will happen? You will use the system in a reversed way. Now, in order to benefit from the stored energy, okay, you can now pass by your water through the thermal mass to take energy from the thermal mass, and then you can use it depending on the need. You can use it for, let's say, for a heating application, or you can use it for domestic hot water application, etc. So this system is combining several strategies: solar heating, thermal mass, and also active equipment in order to control the distribution of energy depending on the time. During the day, we use storage, and during the night, we release back the heat that is stored. Now, of course, space planning is also of high importance. So whenever, for example, you want to simulate a certain building, you need before to do appropriate space planning. And you can study several configurations. So where should we put the bedrooms? Where should we put the living room, etc.? So you can study several configurations. In general, for example, the north face is for service, and it's a transition zone. While you can also create a certain buffer zone that can play the role of entry. The primary occupied zone can be in the middle, and the south-facing buffer zone will be used for passive solar heating since it's exposed to sun during the winter. Now, good interior layout will facilitate many of the passive strategies, in particular thermal mass, lighting, and ventilation consideration. So we should ask ourselves, what are the most frequently used room? What are the lighting needs for each room? And what is the external shading state? And all of this information should be implemented to the energy software in order to simulate the heating and ventilation needs. So in general, for example, kitchen should ideally be located within the building in such a way as to avoid overheating. We can situate the kitchen on the eastern or northern elevation or in a central space within the building. For living spaces in general, we situate them by using rooms on the west elevation, and frequent use of rooms also on the south elevation. For bedrooms, it depends. So we try to ensure comfort depending on the climate zone. Windows should be kept at minimum and should allow for passive ventilation. Concerning mechanical systems, when we design, if you want, a certain map of mechanical systems, we try to place zones requiring mechanical system near each other. So bathrooms, kitchens, and laundry rooms should be placed above or adjacent to each other so that efficiencies of the plumbing system can be maximized. We should minimize the building footprint by using short pipe runs, hot cold water or sewage, and ventilation ducts. In general, we place thermostats with due consideration to temperature variation within the building in order to control the variation and temperature and the operation of active solar systems. Here we can see, for example, how we can optimize the glazing ratio versus energy consumption. So we know that increasing the glazing ratio will have several effects. First, if we consider its effect on heating and cooling, we know that having higher glazing facade will lead to higher heating loads because we have higher sun rays that can enter through the indoor environment by radiation effect, and also will have increased cooling load, let's say during summer, and increased sometimes of heating loads if they are not placed appropriately. Now, on the other hand, concerning lighting load, the lighting load will be reduced significantly by using high glazing ratio, because we know that we can take the advantage of allowing energy, allowing the sunlight to penetrate the space. And then we can calculate like the summation of all heating, cooling, and lighting loads. And we can see that in this case, when we sum all of these, we can come up with an optimal glazing ratio facade. So because we have some loads that are reduced and some loads that are increased whenever we use high glazing ratio facade. So we can select from this graph, for example, an optimal percentage, okay, that can allow to reduce the primary energy use per meter square facade when we design the building. So always we should compromise between the different aspects. So let's say the window can increase some loads but will reduce other loads. So we should find the total load and then find the optimal points that will reduce the energy consumption.
Professor,
Yes.
why does the heating load increase and not decrease, since we're allowing more radiation to enter the space?
Yes, exactly. But whenever, if you consider in some locations, if you want, the window is characterized by a low insulation value compared to the building envelope. So if not selected, if not placed in an appropriate location, and if you increase a lot the area of the facade, the advantage of the window will be lower than the disadvantage. Because if you consider, for example, a certain facade, okay? Let's say you place the window in a good position. It's right that you will allow, let's say on the south face, you will allow energy to come in, okay? But also, whenever you increase a lot this facade, you are creating a large area with lower insulation value, okay? Because at the end, during the winter, you will always have a temperature inside that is larger than the temperature outside, okay? And you have tendency to have heat loss from the inner to the outer space. And in order to reduce these losses, to not have high losses, you play with the insulation of your envelope. So high insulation will reduce losses. But if you use a very large glazing area, okay, what will happen then that the heating load, instead of being reduced, will start to increase. Okay, this is why we say we have a certain glazing ratio. Yani what is the area of the facade that you can take without having a negative effect on heating loads? Okay.
Yes, clear. Thank you.
Welcome. So here, for example, we were discussing now insulation. So we cannot take a large proportion of the wall because the insulation level should be kept high enough. Okay, so we can see here for different regions how we can select appropriately the resistance value. Of course, for moderate climate, the resistance values will be much smaller than harsh and very harsh climate, because in extreme conditions, you should insulate much more than in mild and moderate climates, okay? So as we discussed now, whenever you have extreme conditions, you should avoid as much as possible interaction between the inner and outer environment, because delta T is really high. So the inner, let's say in extreme cold condition, Tn is much larger than T out, and you don't want to have dissipation of heat from the inner space to the outer space. So you should use appropriate insulation levels in order to not have a drop in temperature in your inner space for extreme cold cases. And for extreme warm cases, it will be exactly the opposite. So in extreme warm climates, you will have T in much smaller than T out, and you want to keep this. You don't want to allow a lot of heat to go from the outer to the inner space. So depending on the climate that you have, you decide on the level of insulation that you should put for your envelope. So the R values of walls, including installed insulation and other layers, should lie in the intervals indicated in the table above for small 140 meters square or one-story single-family detached residence. Of course, for each type of building, you have the appropriate R values. So if you study a building with several floors, it's not like the recommendations that you will give for a single residence. Okay, of course. So this is why in ASHRAE catalogs they will specify for you that these are our values for example, buildings consisting of more than 3 floors. This is for single detached residence, etc. So these values are consistent with the result presented in the DOE CS code on the economics of mixing conservation and passive solar strategies. Now, one of the most critical part of the envelope is the roof. And the roof insulation is very important because the roof is highly exposed to solar energy. So this is why we have mainly 3 regions why it is of common practice to employ higher levels of insulation for the ceilings and the wall. The first reason, it is cheaper to insulate the ceilings and walls. Second, temperature stratification will cause larger heat loss rates per unit area of ceiling than per unit wall area. And third, solar gains on roofs during the summer can cause unwanted heating of the living space beyond that caused by high ambient air temperature. So for all of these reasons, we should give special attention to roof insulation, and it should be larger than insulation employed for walls. And of course, this is why in general, for normal buildings, we insulate much more the roof. We do sometimes painting of the roof in order to reduce enhance the reflectivity. Plus, we can use appropriate materials, okay, in order to enhance the roof insulation.
Professor?
Yes.
Would you please explain the second point?
Yes, sure.
And how does the temperature stratification affect the roof?
Of course. You have that when we consider a certain building, okay? When we talk about temperature stratification, you have in the building, you can create like zones of temperatures, okay? So in general, whenever you want, for example, whenever you have, let's say, during the summer, you try to create a lower cold zone and a higher warmer zone. Okay, and you need to preserve within your occupied zone lower temperatures. Okay, now whenever because the roof is exposed to high levels of solar radiation, and it will receive in a direct way the sun rays, because this location will be the most exposed, since you have more chance to have perpendicular rays that will facing your roof. Okay, and this will lead to a high penetration of the sun rays within your system, and this will affect the stratification. It will create a very if you want steep stratification within your space. You will have a very large temperature at this level that will lead at the end, by convection, you might have this high air can go by convection to the lower level and will lead to a higher temperature even in the occupied zone. So by this effect, you are causing, if you want, a higher stratification, and this high stratification created within your space will lead to high temperature difference between the upper zone and the lower zone, which will lead to a warm up even of the occupied zone, and this is not desired. Okay, so and this will lead to a high heat loss rate per unit area of the ceiling, because you will have, if we are talking about summer, you will have overheating, and if we are talking also in winter, you have heat losses from the roof because of the stratification of temperatures that is in the vertical direction. So having an uninsulated wall will enhance this stratification in the vertical direction, okay? Because we know in general that within the space, you have stratification in a vertical way. So this will lead to gradient in temperature in this direction. And high gradient in temperature will lead in winter to high losses of heat through the roof. And also in summer, it will lead to high energy gains through the roof. Okay? So it will play a negative role in both winter and summer. Now, concerning the infiltration, many older buildings have high infiltration rates, more than needed. Of course, we have a certain level of infiltration that is required in buildings because we need to ensure fresh air, to introduce fresh air continuously to the space. But in general, the recommended air change per hour is limited to 1. But if we have more than 1, it will increase the heating and cooling loads. So for older buildings in general, we have high infiltration rates, as high as 1.5 air change per hour. When we talk about air change per hour, so we are changing the whole volume of air within the room. Each hour we are changing 1.5 of the volume air. Okay, while it's recommended to have a reduction to have this air change hour below 1 in order to reduce heating and cooling load. But of course, we should not reduce it to a very small level. So it's not recommended to reduce it below 0.5 because this will lead to low amount of fresh air entering the space. So a reduction to 1 air change per hour may be achieved by employing a plastic vapor barrier. So whenever you have your windows, you can put sealing joints to your windows in order to avoid leakages. So you can seal all joints and form any cracks that can lead to reduction to the level of 0.5 air change per hour, which is required. But as we mentioned, you should not go below this level to avoid reduction of fresh air. So you should have a good indoor air quality within your space. Now, it is strongly recommended that the infiltration rate should be limited to 0.5 air change per hour for both new construction and retrofits whenever possible. And also, this aspect can be introduced to the software that simulate buildings like Energy Plus. So you can specify the amount of infiltration required. Since extremely low rates may be of bad effect to the occupant health due to the accumulation of indoor pollutants, further reductions in infiltration heat loss should be attempted only through the use of window heat recovery units. Extensive use of these units can yield effective infiltration rates as low as 0.187, and under certain conditions, the additional expense involved might be justifiable. So you have some strategies, okay, that will allow, if you want, filtration of air. And this can reduce the amount of fresh air required, because when you filter air appropriately, you can enhance indoor air quality. So you can reduce the amount of fresh air that should enter your space. Now, going back to our solar active technologies. So as we mentioned before, we can use solar water heating devices. It is just constituted by 4 main components. You have the pump that will allow to circulate water within your system. The collector will collect the sun energy, and in the heat exchanger, you can exchange the energy collected from the sun with a storage medium. And when needed, you can circulate water for domestic water heat use in order to supply the needs of shower or any other need of water. And when you don't need it, you can just control this by closing your valves, and then you will accumulate the heated water within your storage tank. So it's very similar